Okay, let's get started. So today we are going to continue our discussion of distributed communication system. But before I start, just a couple of announcements. If you've seen the schedule, you will see that we have our second of our 3 makeup classes this Friday. So we are going to have one more lecture, a third lecture for this week. There will not be a class next Wednesday because I'm traveling. Okay, so I understand that asking you to come on a Friday, which is not really a class day, is a inconvenience, at least for the in-class section. But please come if you can, just to make sure the room, there's enough interaction and discussion going. Of course, we'll record the class and whatnot. And I promise that there'll be only one more after this. Okay, so I rarely have to do 3 makeup classes, but this is one of those semesters. Your question is?
It's same time?
Yes, so Friday is going to be in this room, same time. Okay, and then next week there will not be a class on Wednesday. There will be only one class.
I think the key problem is it conflicts with Candidate Friday. So if anyone has Candidate Friday,
okay, let me think about that. Okay, so there is Candidates Friday this Friday. So I will get back to you on this. I don't know what happens at 2:30. If necessary, I can move it later, or if there's a big problem, I'll have to rethink that plan altogether.
So I know until 3 we have the panel and where all the graduate students will come down.
Okay, so I will not have it at that time then. Either we'll reschedule it. Thank you for reminding me. I have obligations for Candidates Friday as well, but not in the afternoon. So we will either have to do it later in the day, for which I have to first check whether the room is available, or I will have to schedule it another time. Okay, I'm not going to do it next Friday because that's Friday before spring break. Okay, so that courtesy I will afford to everyone. Okay, all right. So let's get started. So today we talk about RPCs and RMIs. Essentially, well, not today. Last time we talked about RPCs and RMIs. Today we continue that discussion, and basically what we will do is raise the level of discussion a little higher and talk about different kind of semantics various distributed communication systems give us, and also talk about very different kinds of communication systems, which include persistent messaging, streaming. We have not talked about how audio video streaming work and so on, and think about how those kinds of distributed applications work. So we'll have 3 modules as usual. The first one is actually going to be on conceptual ideas that tell us how to think about distributed communication systems. Then we'll talk about persistent messaging systems, which is message queuing. And then the last one is on streaming and stream-oriented communication. Okay, so let's start with persistence and synchronicity in communication. So if you take a look at any communication system, and specifically ones that involve distributed application, you can think of communication along 2 axes. Okay? One is what is called persistence, whether the communication is persistent or transient. Okay? And the other one is whether the communication is synchronous or asynchronous. Okay? We already talked some about synchronous and asynchronous I/O and asynchronous and synchronous calls, and so you also have synchronous or asynchronous communication. Okay? So I'll talk a little bit about what each of these axes mean. First of all, what do these terms mean, and then we'll see various combinations of these terms give us very different kinds of communication systems with specific properties. So let's start with persistence. Okay? So what persistent communication means is essentially it is what is called store and forward communication. Okay? Best example is things like email. Right? So if you actually send an email message to someone, it might actually go to the mail server. It's stored there for some amount of time. Then the mail server might deliver it to either the next mail server or the destination mail server. It's stored there for some amount of time until the recipient actually runs their mail client and takes delivery. Okay? This form of communication is called store and forward communication, and the example from the book actually is about the Pony Express, which is how mail was delivered in the old days, and at some high level that's how mail might be delivered now, except that you don't use ponies, but the routing is the same, where you have mail, this is physical mail, not email, arrives at a post office and you sort it and say this group of mail needs to go to this destination, this pile of mail goes to this destination, and so on. And then there is in the old days you actually used ponies to deliver mail. You would pick up that mail and take it to the next stop, and it's stored there. And then some other mail might arrive, and then you re-sort it, and then it goes to the next stop, and so on. Okay, so each hop you are going to store that mail for some period of time. Okay? And in the email case also it was the same thing, where the message was actually stored for some period of time. So you are essentially storing it in a persistent fashion and then forwarding it to the next hop. Okay, so this is called store and forward or persistent communication. Okay. Mail system, not mail, communication systems we have seen so far have not actually used persistent communication. Okay. We have not actually had any store or forward examples yet. Today we are going to see some. Okay. Now the other side of persistent communication is non-persistent, which is actually called transient communication. Okay. Here the network is not going to store messages for arbitrary periods of time. Okay. It is assumed that the sender and the receiver are both executing, and messages can be sent and then be delivered to the other end as soon as it's received at that machine. Okay. So you don't have, so if the recipient is not executing, the message cannot be stored. It will actually be discarded. Okay. Unlike email, if you have received an email, the mail server is going to store that message for you. It's not going to say there is nobody checking mail, so let's discard that email. That does not happen. But when you send a TCP packet, or even if you try to make an HTTP connection to the web server, if there is no server application running, your message is going to be dropped and you're going to get an error. Okay. So this is called transient communication. There's no storing of messages. You basically route the messages and deliver it as soon as it reaches the other end. Okay, is that clear? So, TCP and other protocols essentially fall into this category. They are more they use transient communication for the sender and receiver to communicate. Okay. So that's one axis, whether it's persistent or transient. The other axis is whether it's synchronous or asynchronous. Okay. Synchronous always means blocking communication. Okay. So what that means is when the sender sends a message, it is going to block until some sort of an acknowledgement or a reply is received. Okay, so that's blocking. Asynchronous always means non-blocking. So you can think of synchronous as being a synonym for blocking, and asynchronous being a synonym for non-blocking communication. Okay. So when you have asynchronous communication, you can send a message and not wait for any acknowledgement. You can just continue execution or continue to do something else. Okay, so essentially you have synchronous or asynchronous. So now if you take these two axes and put them together, you are going to at least get 4 combination of whether the system provides transient or persistent communication, synchronous or asynchronous communication. Okay, and in fact, we will see that some of these actually have multiple flavors. So we are going to examine not 4, but 6 different flavors of combining persistence and synchronicity. Okay, we are just going to do this with pictures and some examples. Okay, so the first one is persistent and asynchronous. Okay, that means you are going to have store and forward, and asynchronous means non-blocking. Okay, so that's shown in this picture. You have machines A and B or applications A and B that are communicating. Again, x-axis is time. Okay, dotted lines mean that that party is not executing. The thick lines essentially say that you are executing. So here you have A is executing some code, then it sends a message. Okay. But because it is non-blocking, it is going to continue as soon as it's done the send. It's not waiting for a reply or anything of this sort. Okay. That message is actually going to be sent and received at the other end, and because there is a sort of broken arrow that indicates that it's store and forward, it may take an arbitrary amount of time, but eventually it is going to be received at B. Okay, and then B at some point will take delivery of that message and continue. Okay. Example of this form of communication is email. Okay, when you send an email, you don't wait for a reply to be received, you just go to something else. Okay, and the recipient will take delivery of that email message at an arbitrary later time. and they check the email next, for example. Is this clear? Okay. So that's persistent and synchronous, or rather asynchronous. The other one is persistent and synchronous communication. Okay, so here the only thing that has changed is you are essentially going to have blocking calls. So you still get store and forward, but you have blocking. So here you will see that A sent a message and it blocks. The message reaches B, and then you get an acknowledgement, okay, and then A can continue. Okay, so you are going to block and wait for an acknowledgement to be received before you continue execution. Okay. But because this is persistent communication, at B you are going to store that message for some arbitrary period of time until B decides to take delivery of that message. Okay. So that's the only difference between the two. There are many systems that do this. Okay, we'll talk about message queuing systems in a little bit. I'll do this, but think of if there are certain email systems that actually give you delivery acknowledgement. Okay. There are certain chat systems that also tell you whether your message has actually been delivered or not, and if the person has actually not read your message. Okay, so you get an ACK even though the message may be buffered for the recipient to take delivery. Okay. Those are some examples of persistent synchronous communication. Any questions on this? Okay. So the next one is transient communication, or all of the next few ones are all transient communication. So we'll start with transient and asynchronous. Okay. So here there's no more store and forward, and asynchronous essentially means non-blocking communication. So you will see here that A is going to essentially execute, send a message, continue execution, and the message is going to be received at B while it's executing, and it takes delivery of that message. So there's no acknowledgement, there's no blocking of any sort. Okay. UDP communication is an example of transient asynchronous communication. Okay, so if you use UDP as a protocol for communication, you will essentially get this property. Okay. So now the next three are going to be variants of transient synchronous communication. Okay, so again it is going to be no store and forward. Okay, and because it's synchronous, you are going to block and wait for an acknowledgement. Okay. Now the three flavors that we will see essentially differ in the following way. Basically the acknowledgement conveys different things in the three systems. Okay, so what is the ACK telling you? Based on that you are going to get three flavors. Okay. So the first one is receipt based transient communication, where the ACK basically tells you that your message has been received at the other end. Okay. So here you will see that A sends a message, it blocks. Okay, because this is synchronous communication, the message is received, you get an acknowledgement, then you continue. Okay? And then here you are basically going to have B is going to take delivery of the message and process it. Okay? So in this case, the ACK says the message was received. Okay, now we have two more variants of this, where you have delivery based, which says that the ACK not only tells you that the message was received at the other machine, it also tells you that the message was actually delivered to the application. The application has actually taken delivery of the message, not just sitting in the OS buffer. Okay, so here you will see that you wait until B starts processing the request, okay, and then you send an acknowledgement. So you are blocked until B has actually taken delivery of the message, not that it just got to machine B. Okay. So that delivery based. The third one is response based, where the ACK actually comes back with the response, which says essentially that your message was not only delivered, it was processed. So you wait until it was processed. Okay. And you will realize that the third one essentially is what RPC does. Okay. Standard RPC is going to cause a request to be sent. The sender is going to be blocked until the RPC returns. Okay, the return of the RPC call essentially says that your message was received and processed, the RPC executed. Okay? Is this clear? Any questions on this? Yes, question. What's your question? When will the message get lost? Okay. So in these cases, we are assuming that the network is not dropping messages. It's a conceptual description, of course, right? I mean, we are not saying how to implement this, so we are not worrying about packet losses and so on. So another way to think about this is, let's say you're using TCP, where this arrow simply means that TCP sent the message to the other end. That's one way to think about it. But don't worry about network losses, because this is without failures at the moment. Okay, question? Okay. Question is, we said that the last one, which is response-based transient synchronous communication, is the same as an RPC system. Or is a RPC system is an example of this. And the question is, what if the server is actually not running, right? So if the server is not running, first of all, the RPC will not even go to the server because you won't be able to bind to the server. Okay, because the way RPC systems work is server comes up, it registers itself with the naming service, and then when the client comes up, it does binding, which is looks for the server and figures out where it is running. Okay, so you wouldn't even get this far if the server was not running. Having said that, if the server did start up, it registered itself and then it crashed, maybe it's still registered, the client might try to make a connection, but it will get an error because the port will not actually have an active TCP listener there. Okay? Any other questions? Okay. So I want to go back to a few slides that I showed last time, and we are going to try to map these systems to, we already mapped RPCs. Now we want to think about what is, this is basically TCP based socket communication. As it already says there up there, it is essentially transient communication. It's not persistent, it's transient. So then the question is, which flavor of transient is it? Is it synchronous or asynchronous? Are you going to do blocking calls here or non-blocking calls? Yes? Sockets are blocking. That's good. So this is basically just very standard socket calls. They're all going to be by default synchronous. Okay, they basically block until you get at least some sort of an ACK. Okay? So that's the simple sockets. But now if you go to MPI, which is what I ended with last time, I'm not going to repeat this slide. I already went over it last time, but I do want to come to this table, which gave us very many flavors of send and receive. Okay. We said that MPI, which stands for message passing interface, has 7 or 8 variants of send. So B send says append that to the local buffer, send says wait until it's received at the remote buffer, then wait until receipt starts, wait until you get a reply. So you will see that these variants are actually mapping to the flavors of transient synchronous communication that we were talking about. Depending on what the ACK tells you, either the message has been received by the remote buff machine, it has been received by the application at the remote end, or you actually waited for a reply. So those 3 flavors actually directly map onto this. Of course, you also have the asynchronous one where you simply give it to the OS and you continue. You don't actually do anything. Okay? So MPI actually allows you to choose what kinds of combination of synchronous communication you want to use for your sending and receiving. Okay? So you can use blocking or non-blocking. Essentially, the first one is non-blocking because you're simply going to give the message to the OS and continue. All the other ones are blocking. Okay? Receive also has a blocking and a non-blocking version. So you will see that the standard receive is blocking. You'll wait until you get the message or get a message. And I receive is simply going to be the non-blocking version, is checking or polling if there's a message. If not, you just return saying there is nothing in your socket buffers. Okay. So what this should illustrate to you is MPI is a much richer communication system where as a programmer you can decide what type of communication is most appropriate for whatever application you are trying to build. If you are using simple sockets, you are only left with one choice. Okay? Of course, you could use UDP that gives you second choice, but beyond that there isn't much else you can do. Here you get this entire spectrum of choices. Okay, any questions on this? Okay, so we will continue. This is the end of module 1. So we will continue the story I had said a few weeks ago actually. So this is the part 2 of Lion and the Rabbit. If you remember, there's a lion and a rabbit in the story, which is why it's named that way. So the story continues as follows. Now it's actually lion that is going around in the forest. Lion meets a fox, and the fox looks worried. And the lion says, "What's the matter?" The fox says, "I damaged my watch, and it's a really fine instrument, so I don't know what to do." So the lion says, "Let me repair it for you." Okay, and then the fox says that that doesn't seem possible. Your claws are thick and fat. This is a very fine instrument. I don't think you can repair it. So the lion says, give it to me, and then goes into the cave and comes back out, and the watch is all fixed. Okay, then a little while later, the lion meets a wolf. The wolf is also worried, and then the lion says, what's the matter? The lion says, I was typing a paper, but my laptop disk crashed. Okay, so the lion says, let me fix it for you, and I'll recover your data. Then the wolf says, how is that possible? You can't even type. How can you fix a laptop? Because your paws are thick and fat. So then the lion says, let me take it and fix it for you. Goes to the cave, comes back, and the laptop is fixed. The data is all back. Okay? And then inside the cave, there is a group of rabbits, which in this case are grad students. Okay? And then the moral of the story is, it doesn't matter what your advisor knows or doesn't know. It really matters what the student knows and can do. Okay? So, all right. So now that we finished our story finally, we'll continue with module 2, which is we are going to take persistent communication, which is what we really haven't seen until now, and start digging deeper. Okay, we are going to talk about what kinds of systems. I said email is an example, but email is not really a system you use to write application. That's an application itself. What kinds of communication systems can we use to write applications that use persistent communication? Okay, so we'll essentially use message queuing systems as our canonical example. Okay? So I don't know if anyone has actually used an MQS system. If you heard of things like Kafka, okay, that provides message queuing. There are other systems like ZeroMQ, RabbitMQ. IBM has a message queuing system. Microsoft has message queuing system. So these are all systems that have very specific flavor. They do not use TCP-like communication. Okay, they have queues where messages can be buffered for arbitrary periods of times. These are not in-memory queues. They're on-disk queues. Okay? So if a message arises stored on disk, so that delivery can take place at a later time, it can be stored for arbitrary periods of time, and so on. Okay? So they all provide store and forward communication. At each hop message is received, it will be stored in an on-disk queue, and then the next hop can take delivery of that message at an arbitrary later time. Okay? So the communication from end to end might take arbitrary amount of time in a message queuing system, and there will be queuing delays along the way that is going to take up some of this time. Okay, so it's best. So the guarantees here are that eventually the queue is the sender, the recipient rather, will see the message. Okay, but whether the message will actually be delivered, you don't know. It might sit in that queue for an arbitrary period. It's the same as email. Just because you sent email, there's no guarantee it will actually be read. Okay, the person may never open their email. There's no guarantee that they'll actually read it. So the same is true here. Okay, so here is a picture that shows various combinations that may occur. Okay, so when you send messages, so first one is where both the sender and the receiver are actually executing while you send this message. And this queue here is shown as a logical message queue. As we'll see in subsequent slides, you actually have a sequence of queues because you're doing hop by hop delivery. But that entire network is represented by a single logical queue, or an abstract queue in this case. But what is more important is when this sender has sent the message and the receiver has received it, both sender and receiver are actually running. Okay? In the case of transient communication, that is essential. Okay? If the server is not running, you can't send a HTTP request to the server and sit there for days until the server comes back up. None of that actually works when you have transient communication, but here that is entirely possible. Okay? So, but in the first and the most simplest case, both of them are executing while communication takes place. Second scenario is where the sender is running. It sends a message. Message comes and sits in this abstract queue. The receiver is not executing at this point. It's not even running. At some later point, it might come up and start running and then take delivery of the message. Okay? That email is a good example of how this might actually happen. Okay? In the second case, you actually have the message has been sent, but all it's illustrating is when the receiver is taking delivery of that message, at that point there is no requirement that the sender be running. Sender has already done its job, send the message, so it may not be executing. And when you read email, you would expect that the sender is sitting there still active on their desk. Okay, so same thing is true here. And then the fourth case shows where the queue has actually buffered your message for an arbitrary period of time. Neither the sender or the receiver are executing, and the message will sit there for as long as it needs to, until eventually the receiver runs and you are in one of cases B or C. Okay? So you might get all of these cases which you won't see in transient communication. Transient communication, you are basically in scenario A. Okay, here you have the spectrum of scenarios of what might actually happen when the message is being routed through the network and so on. Okay. Now the message queuing model at its core is extremely simple. Okay, you have an abstract notion or a data structure called a queue, okay, which is a persistent queue. That's the most important part. Okay, it's an on-disk queue, and all communication is going to happen through two calls, get and put. Okay, so put allows you to insert a message to a queue. Of course, when you do put, you have to name the queue because there may be many queues. Just as when you send email, you have to name the recipient. Okay, and the inbox is an example of a queue, just from a conceptual standpoint. Okay, so you essentially have a queue, and you're going to use get to insert a message into the queue, or sorry, put to insert a message into the queue, and get to remove a message from a queue, or remove the message from the head of the queue. Okay, those are our two canonical calls that we are going to use for communication. Just as we had send and receive for transient communication, we have get and put for persistent communication. Okay. And then there are some other calls that you could use for additional features. You can, if you want to do this in a non-blocking way, you are going to use poll and notify. Okay. So poll essentially checks a queue to see if a message has arrived. Okay, just as your email client might periodically check the server to see if a new email has come. Okay, that's a form of polling. Okay. And notify is an asynchronous message from the queue to the receiver saying a message has arrived. So you are actually getting notified. You don't have to poll, because polling is a periodic process. Okay, if messages are infrequent, you might waste a lot of resources polling and getting a notification saying there's nothing in the queue. So rather than do that, you might tell the queue saying notify me if something arrives. Okay, so these are both going to allow you to essentially use message queuing systems in an asynchronous fashion. But even without that, you can still implement them using synchronous calls like get and put. Yes, question.
For actual applications, fault tolerance, do they write to disk before they notify the
Right. So question is, for fault tolerance or reliability reasons, are you going to write to the disk before you are notified about something? Right. So typically you will have to do that. Right. So when the message comes, you are going to write it to disk, and then you might acknowledge it or some such thing, or even send a notification saying a message has arrived. That is how most of the systems would do it. Okay, there's some other question here. Yes.
What was the second part in the column?
What does poll mean exactly? So check for a message, check for a queue for messages, remove the first, meaning remove the message at the head of the queue. If there is a poll can return with a message. It doesn't have to just tell you whether there's if the queue is empty, it will say there's nothing. But if there is a message in the queue, it will actually take a message out and give it to you, just as get would do for you. Okay? So basically, if the queue is non-empty, it's going to be the same as a get. Okay? But if the queue is empty, this will not block, but a get will block until a message arrives. That's the difference between the two. Okay? Yes, go ahead. Right. The question is, do poll and notify go hand in hand? Both will allow you to essentially communicate using MQs in an asynchronous fashion. Okay? You still need to do put to insert messages. This is just about taking messages out of the queue. So there isn't one that does asynchronous puts. There's just one put. But rather than use a get, you can either use a poll or you can use a notify. So these two can be thought of as a, well, not both. Poll will basically check and take messages out. But what notify will do is you will be told that there is a message, and then you will use a get to take that message from the queue. Okay? So that, because that get will be non-blocking, it will just take the message and not block if the queue is empty. Okay, any questions here? Okay, so that's basically the simple abstractions for message queuing system. That there are lots of systems that will be fairly complex in how they're set up. Here's an example of an application that has been built using message queuing system. Okay, so you will see that there are all sorts of queues. So there are 4 components to this distributed applications that are shown with the box called application. And then there are these components in the middle that are called routers. They are not network routers that do TCP routing. They are message queuing routers that basically essentially deliver messages for MQS systems. Okay? And you will see that each application has a send queue and a receive queue. Okay, to send messages out to any of the other components, and the receive queue to receive messages from any of the other components. Each of this is persistent. Okay, once you send a message, okay, when you do a put, you have to specify a recipient for that message. Okay, just as when you send an email, you specify an email address. Okay, you are going to essentially put it in a queue, which is essentially the ID of the queue or the recipient, and then it's going to go into this outgoing queue. Then it's going to be going. It will go to the first router. The router will say what's the next hop, and each hop will basically do store and forward delivery until it reaches the endpoint. Okay? And then it will sit in the receive queue of that endpoint, and then that application can take delivery at some later time. Okay? So there is this router elements in the middle essentially do provide persistent queuing. Okay? The end queues, the send and receive queues at the end application also provide persistent queue. Okay, between each hop you can use get, put, poll, notify to essentially communicate and send the message one hop at a time until it gets to the destination. Okay? You also need a routing protocol. If you get a message from a previous router, you need to know where to send it next, so it eventually gets to the application. Okay, that routing protocol is similar in flavor to network routing protocol, but we won't get into the routing protocol here. Okay, is this clear? Okay. So there are many commercial MQS systems that will be built like this, and they are used for applications like order processing and so on, where or business to business B2B applications where there's messaging between different components where the messages have to be persisted and they can be processed at later time and so on and so forth. Okay. All right. So the other component that you see often in a message queuing system is called a message broker. Okay, or so essentially very simply just a broker. What this does is it's an application level program that can take messages from a queue and perform some transformation on the message and then send it out. Okay, so it can do things like translation or many other things like format conversion and so on and so forth. Okay. They're also going to be used in publish subscribe systems. Okay, so for example, if a message comes in and there are many recipients who are interested in a certain type of a message, they can subscribe to those messages, so that message might get delivered to multiple recipients at the other end, for example. Okay, so we'll come back to publish subscribe system at a later time, but if you have need for publish subscribe, or you just have to need for doing some conversion, protocol conversion or format conversion of the message, you are going to take the message, the broker program is going to execute and transform that message, and you'll send it out again. Okay. So these are called message brokers. We'll come back to brokers that do other things at a later time when we talk about middleware system. Okay, but this MQS is also type of a middleware system incidentally, and that is why you have brokers in here as well. Okay, so this is an example or a picture that shows you a commercial message queuing system. There are many open source ones like Kafka and others that I have talked about, and you will see this is IBM's WebSphere message queuing system. It has some of the elements that we talked about. Okay. The interesting thing here is you will see I essentially start seeing stubs at each end. So the get and put are implemented as remote procedure calls. That is why you see a stub. So each element is using RPC to communicate with the next element. Okay, and you will see that this is a sender, this is a router. There are many other routers here that are not shown. So the second router, that's the receiver. Okay, so you will see here essentially you are going to take the message and put it into an outgoing message using an RPC call. There are multiple queues. You'll put it in one queue. There's a routing table that's shown that tells this router where this has to go. In this case, it's just going to the next one. And then once it gets received here, the client program is either going to do a get or a poll to essentially extract that message and take delivery. Okay. So I mean, of course, it can be more complex than this, but this is a simple example of how you used RPCs in this case to implement get and put or higher level message queuing system. Of course, the queues actually have to be persistent queues. They're not in-memory queues. Okay, all network routers only use memory buffers. The TCP packet is never going to be stored on disk typically. It's only going to be going from memory of one router to the other until it reaches the OS. Even in the OS, it's in the buffer, the memory of the machine, okay, never on disk. Here all the queues are persistent. Messages are essentially going to have to persist on disk because they can be stored for arbitrary periods of time. Okay, so that is message queuing system, and in the remaining time that we have, we are going to actually talk about a very different kind of communication, which is not request reply or not message driven, it's stream based. Okay? And you've probably seen all of this if you've used audio or video applications, whether it's YouTube or Netflix or any audio streaming service. They are all going to use some form of stream communication. Okay? So let's try to understand first what is the difference between message communication and stream communication. Okay, so all message communication can be thought of as a request response. Okay, you make a request, you get back a response, and so on. Okay. In stream communication, that's not how things work. Okay, so essentially, you may start getting data without even it being requested. Okay, so think of video streaming. Once you say play, the server will actually send you data. Okay, and then you just have to receive it and then decode it and play it out. Okay. That's essentially how stream communication works. But as I will show you later on, that is how video streaming was designed long time ago. Today's video streaming actually goes over HTTP. It has actually become request response. But conceptually, you can think of streaming as a mode of communication where you basically keep getting data from the server asynchronous without actually having to request it. Okay. Now, but there are many other important aspects of stream communication when they pertain to audio and video. The most important one is that there are timing constraints. Okay. If you are playing a movie, okay, from YouTube, say, or Netflix, if the data for the next part of the movie that you are about to play out doesn't actually arrive from the network on time, you are going to get a playback glitch. Your playback will freeze. Okay. So that essentially your correctness of your application now depends on timely delivery. Okay. When you are actually doing web browsing, okay, even if the response is slow, that does not impact correctness. Okay, you're just getting slow responses. Here, you are actually going to have an impact on correctness of your application. You are going to get things like playback glitches and so on. Okay. So essentially, this form of communication is called isochronous communication. There are timing constraints. Okay, if you are doing 30 frames a second video, right, so that means there are 30 images every second. You essentially need every frame, the next frame to come every 33 milliseconds, but there are 30 of them every second. Okay, if they don't arrive, then your playback buffers will empty out and you are going to get a playback glitch. Okay. So there are strict timing constraints. What that means from a network perspective is that the end-to-end delay that a packet sees or your frame see can't be arbitrary. Because if they keep fluctuating, then you might see problems at the other end where you're not receiving data on time, and hence your video or audio playback is going to suffer. Okay. So that's one characteristic. The other one that I actually was mentioning was stream communication is essentially not client pull. Message oriented communication is request response or client pull based. Stream communication is typically server push. A server is taking charge of pushing data to you. Okay, so now let's talk a little bit about various types of stream communication. So there are many flavors of streaming. Okay. The two canonical ones is live and stored. Okay. Live streaming is like video conferencing. Okay. Essentially, the two parties are both live. Okay, there are two cameras and maybe two microphones at each end and maybe speakers, and they are capturing the images and audio live. They're encoding it, transmitting it over the network, and this being received in real time at the other end. Okay. There are strict constraints on this kind of communication. If it takes too long, then communication is not going to be very effective. Okay, because you might say something and wait for a while, okay, and then you don't hear anything back. You said, did you hear me? But if it takes a long time for the network to deliver your message, that's maybe what the problem is, not what the other person is not able to hear you and things of that. Okay, so when you have live streaming, okay, the end-to-end delays have to be in tens or hundreds of milliseconds. Typical human perception essentially requires 150 milliseconds. Okay. If I say something, Okay? And you don't hear what I'm saying within maybe 150 milliseconds from when I said it, you might actually start perceiving problems in communication. Okay? Same thing happens on phone, or if you're using Skype and things of this sort. Okay? So there are fair timeliness or end-to-end bounds that you need to impose when you do live streaming. Okay? The other type of streaming is what is called stored streaming, where the data has actually already been created, is stored on a disk on the server, and it's just being streamed to a person who's watching it. Like this is what would happen when you use YouTube and Netflix. One endpoint is not a live person, it's actually a disk that stores your data, and the server is simply streaming it to you. Okay? Here the end-to-end delay actually does not matter as much, but so long as you're getting data at a steady rate, that is what matters. Okay? In live streaming, you need both. You need data to come at a steady rate, but the end-to-end delay, because it's live communication, also has to be small. Okay? So that's one axis, whether it's live or stored. Okay? Then the example, there's an example of live there. The other axis is whether it's one-to-one or one-to-many. Okay? The top one is essentially one-to-one. Okay? There's one sender, one receiver. Okay? But there is many kinds of stream communication where essentially is one sender, multiple receivers. Okay? If you're doing a webcast, okay, you're basically watching a live stream of, let's say, sporting events. There's one server, but there may be tens or thousands of users or millions of users that are all tapped in. So the data is actually flowing to lots of different recipients. So there's one sender, many receivers. Okay? So that's essentially multicast streaming. Okay? Streaming to a large group of users. Not that there's only one recipient, there are many recipients. Okay? So there are different flavors of this. We are not going to look at every single variant, but we'll go into some details of what you need to do in order to make all of this work. Okay, any questions on this so far? Okay. So let's think a little bit about how your network is supposed to give you all of these timeliness guarantees and so on. Okay, so when people started thinking about streaming video over a network or audio over a network, they said best effort networks are not going to work. Okay? Internet, as you know, is a best effort network. It gives you no guarantees at all. Okay? It doesn't tell you whether your packet will be received, what kind of delays it will see, and so on. Okay? So in the early days of streaming, researchers said that is not the right type of network architecture. What we need is the network needs to provide us harder guarantees. It needs to allow us to say, I need so much bandwidth from the network, I need this kind of delay, and this kind of loss rate, so I can actually get a good quality stream from the sender to the receiver. Okay? So to convey to the network that these are the properties you need, they came up with this notion of quality of service. Okay, which is called QoS, if you ever heard of this term. These days also called QoE, quality of experience. That says what quality should I get from the network in order to get good quality streaming. Okay? And the quality of service is simply a set of metrics that says this is the performance I want from my network. Yeah, so you could say I need a certain bandwidth. This is a HD video. You at least need 1 megabit bandwidth for you to actually watch HD quality video. If you have half a megabit or your low, slow cell phone connection, you may not be able to get HD quality video. Okay? So that basically says what is the minimum bandwidth the network should provide in order to be able to stream this kind of data. Right? So then you might say I need 100 millisecond end-to-end delay. Okay, this is basically, let's say, live video conferencing. You may be doing Skype or FaceTime or whatever your favorite video conferencing application is. You said for good quality I need such a max end-to-end delay bound of something. Okay, so that's another metric you might specify. You might also say I want lower loss rates. Okay, because there are timeliness constraints, if your network starts dropping your data or packets, there's no time for you to retransmit. Okay, because clock is ticking. Right? Typically in TCP, if your data does not make it to the other end, you will have a timer, you will get a timeout, you will retransmit. Eventually your data will get there, but there is a certain amount of time has elapsed. Okay? In video streaming, that's not going to work because you want data to come in a timely fashion. The data is lost and retransmitted, that's too late. Okay? You already have a playback glitch. Okay? So you want low loss rates as well, and you can specify that characteristic. I need a good quality connection, low loss rates, and so on and so forth. Okay? So you can have a number of metrics that you can specify for QoS, and here's a table that says what kinds of metrics can you specify and what kind of service do you see. So this is basically what the data looks like, and I'll talk about this in a moment, and that is what you want from the network to get this type of stream across the network with good reliability. Yes, question?
Can you go back to the previous slide and can you explain the difference between end-to-end delay and a round-trip delay? So isn't the round-trip delay just the end-to-end delay twice?
That is indeed true. So this is one way, and that's round trip. That's sort of the.
Doesn't one of those properties actually define the other end?
Okay, so question is, that's a good question. Question is, does end-to-end, if it's one-way delay, define what the round-trip delay is, right? So the answer to that question depends on whether the network has the same properties bidirectional. That does not have to be the case. If I am doing Netflix streaming, what is more important is the delay from the server to the client. The reverse doesn't matter to you, right? But if you are doing video conferencing, you care about delays in both directions. Right, so the network in one case is provisioned well along the forward path, in the other case it has to be provisioned in both directions. So it will depend on what kind of streaming you're talking about. Right? Question?
I would also interject that it matters the processing that's happening on the ends. So if you have to do a bunch of processing and you're not fast enough,
Right.
round trip delay.
Yes, so the point that is being made is in the round trip delay might actually involve processing, and depending on the processing that might change. That is indeed true, but this was just network RTTs. This metric did not actually include the processing time, but typically when you're looking at web server RTT, you will include processing. This is just TCP RTT. Okay, so there's a difference, but what you said is right. Any other questions here? Okay. So the way the network architects envisioned this would happen in the old days was that the client would say, this is the kind of data I want to transmit. Okay, it's HD quality video. It takes 4 megabits. Okay, this is the quality loss rate I want. This is the end-to-end delay I want. So you would specify your input characteristics, which is the type of data you want to send, and then you would say, this is what I want the network to provide to me. Okay? And then the network would see if it has sufficient resources to guarantee you that quality. Okay? And if so, then you basically have a contract between the end client and the network saying, if you transmit based on what you specified, you are going to get the quality you requested. Okay? So that's a contract. Okay? And then the network would guarantee you that. Okay? There are many network protocols that were designed to do this. Okay? At the end of the day, none of them became commercially viable. The main reason for that is really sort of a networking argument, which say if you want to actually provide guarantees, you want to put state in the network. Okay? But essentially the way the internet has been designed, state is only at the end point. There is no network state inside the network. The routers don't keep state. And if you keep state that's inside the network, you basically will not be able to scale to lots and lots of connection. Okay? So this actually never came to pass. Okay? The networks today are still best effort. They don't give you any of this. But there has been a lot of work done on it. Okay? Now, although networks don't give you quality of service guarantees, there is some of this work does apply to end host. So you can actually get guarantees from your operating system for running applications. You can ask for CPU guarantees, you can ask for network guarantees and so on, which is used in things like virtualization. Okay? We said you can allocate a certain amount of RAM or network bandwidth or CPU to a VM. That essentially uses OS level quality of service. Okay? So network QoS actually never went anywhere at the end of the day. It's just historical perspective from what happened in research. And lots of papers were written and got wasted because nothing ever actually became commercialized or operational. Okay? But it is still instructive to at least see if you are asked to provide a certain type of QoS guarantee, what would you do to actually provide it? How would you enforce it? How would you make sure that you are actually going to be able to provide some guarantees at all? Because this is still, these ideas apply in other contexts like operating systems. Okay? So I'm going to show you one mechanism to provide quality of service. Okay? It allows you to specify and actually guarantee that quality of service, which is called a token bucket regulator or a leaky bucket regulator. Okay? This allows you to guarantee a rate. Okay? The rate could be CPU percentage, it could be a network bandwidth rate for a client. from a end host. Okay, and I'm going to come to that picture in a moment, but let me explain what this actually means. Why is it called token bucket and so on. Okay. So essentially, the way you specify a token bucket is there are two parameters. Okay, average rate R, okay, and a burst size B. Okay. So any token bucket has two parameters associated with it. Okay. A rate at which you are going to send and a burst rate B, which allows you to instantaneously send more than that rate. Okay. And what this rate does is it basically says at any time t, starting from 0, the amount of data I can send is essentially going to be bound by essentially the rate times t plus the burst size B. Okay, so if you want to see this in a picture, essentially this is going to say this is basically the line that says RT plus B. That's the y-intercept is B. That's the x-axis is time. Okay, the y-axis is the amount of data sent at any time. So what the token bucket regulator will do is it will guarantee you that the amount of data you send will essentially be below this curve. You will not be allowed to exceed this curve at any time t. Okay. So essentially, if the simplest thing is if you set the burst size to 0, okay, you are going to send at a constant rate of R. So this basically says I can only send at a rate of R or lower, but never higher. It's going to basically prevent you from sending at a higher rate if you try to send. But you can always send at R or anything lower than that. So you will basically the network is going to enforce that rate for your connection. Okay, but you can essentially specify a burst rate B, which will allow you to send at RT plus B. Okay. Now, the way this is implemented, okay, so that's just the conceptual or the theory behind token bucket, but the way this is implemented is what is shown in this picture. Okay, so this is where this notion of a token bucket or a leaky bucket comes in. So it says that, let's say you want to send an application is sending some network packets out. It's sending some data on a network. Okay. Every packet, before it goes out, it has to get a token. The token essentially gives it permission to be sent out. Okay. If there's no token available, it has to wait until the next token actually gets generated. Okay. And you are essentially going to generate tokens at the rate of R. R tokens are going to be generated every second. Okay. And essentially you are going to initialize your bucket with B tokens. At time 0, you will start with B tokens and you start generating R tokens every second. Okay. You can have no more than B. If you basically don't send, you don't keep accumulating tokens. The maximum amount of excess tokens you can have is at any time is B. Okay. And then you keep generating R. So if B was 0, you'll just start with 0 tokens and you'll generate R tokens every second. You generate a packet, it has to see if there's an available token, it grabs it and it goes out, and then you have R minus 1 left, but you keep generating. Okay. If you send a burst of packets, all your tokens are out, then your packet has to wait until 1 over R seconds when the next token is generated. Okay. This is how you are going to essentially enforce that the rate at which you are going to send is going to be bounded with the average rate of R and a burst size of B. Is this clear, what I just said? So this is how you are actually going to implement that mechanism, the notion of token bucket, into an OS. You are going to essentially have tokens, and then packets have to essentially grab a token before they are allowed to be sent out. Otherwise, they are going to be queued up. So you are sending at a rate greater than R times T plus B. Okay, so this allows you to enforce a rate on your sending. Yes, question.
Where does the buffering usually happen?
Okay, so where the question is, where does the buffering happen? It's going to happen in the device Ethernet device driver.
The application that's sending it, does it block when the bucket is full, or
Right.
is there
Okay.
additional memory that's
Right. So the question is, if the token bucket is empty, not full, will the application block? So this is all invisible to the application. This is OS level mechanism. Application is going to do its thing and keep sending. Okay, the messages are going to, packets are going to come to the TCP buffers, or in this case they'll be at the device driver buffer, and they're going to be essentially wait for a token if one is not available, or they're just going to take a token and be sent out. Okay. So essentially, if you send at a faster rate, your queues in the OS are going to keep filling up because you don't have enough tokens. You're not generating tokens at a rate fast enough for you to send all the packets. They'll start backing up in the OS buffers. eventually your buffers will fill up, OS application will get an error if it tries to do a send on a socket. Okay? Yes, question.
It sounded like we defined the quality of service measures as like lower bounds, like you would exceed this performance, but then this seems to be like an upper bound.
Yes, that's a good question. So here, so the question is, can you specify QoS as a lower bound or an upper bound? This is simply an example of an upper bound. In fact, this is the same thing that you will use if you had a virtual machine. Let's say 2 VMs running on a machine, right? And you want to say, I have a gigabit Ethernet card. I want to give maybe 500 megabits of bandwidth to VM1, 500 megabits to VM2. You can use a token bucket for each of those VMs, so they can never exceed their rate. This is how you are going to take a bandwidth of a Ethernet card and partition it among 2 or as many applications as you want. Okay? So there are many reasons why you want an upper bound. There may be reasons you want a lower bound as well. This mechanism won't give you one. There are other mechanisms to do. This is just a simple mechanism to show you how to enforce QoS. Okay? And in fact, similar mechanisms are actually used when you try to take a physical Ethernet card and partition it among multiple VMs, for example, and each of them gets a dedicated allocation that's enforced using this mechanism. If you try to send faster than that, you will actually not be able to do it. Okay? Question, yes.
Is it right to assume that the main advantage of the burst is like when you have a cold start and you're just starting up?
Okay. So question is, what is the main advantage of a burst size? Why do you want to do it? Okay, the burst size is simply allowing you to, for small amount of size, send faster than that rate, because you might never actually want to send at a steady rate. Okay, so you can decide how deep the burst size should be. Okay, if you set it to a large value, you can instantaneously exceed that the rate of R for some period of time until you actually empty the bucket. And that point you're stuck at sending only at R, because there's no tokens are only getting generated at R. Right, so it allows you some variability in how you send. Any other questions? Yes, question there. When do you regenerate burst tokens? You are never there are only one kind of tokens. There's no such thing as rate tokens and burst tokens. So essentially you initialize your token bucket with B tokens. Okay? And then once the clock starts ticking, every 1 over R seconds you generate a token and you add it to the bucket. And the bucket depth is B. So if bucket is full, that token is wasted. You're not going to do anything. But if some of the bucket tokens have been used that you initialize, then you keep adding 1 over R. Okay? So you will not regenerate burst tokens, except that if the application doesn't send at a rate of R, it sends at a rate slower than R, then you will generate tokens faster than your packet send. So your tokens will start accumulating again, and you can accumulate at most B. Right? So that's how you will actually get back your burst capacity. You have to actually send at a rate lower than R, so you will keep having surplus tokens that keep building up.
The maximum amount is B tokens and R is larger than B, so every other token gets invalidated.
Yes, so if you filled up B, because you can never send more than B at once, right? So that allows you to send B packets out immediately. So if you already have B excess tokens, and you're still generating at a rate faster than you're sending, you're not going to keep accumulating. That tokens get wasted. Okay, that's like saying, I have idle bandwidth, I'm not using my allocation. Okay, you don't keep accumulating credit so you can use it at a later time. Okay, credit is only B of how much you can accumulate or how much you can send at the same time. Okay, any questions on this? So it's a very popular networking mechanism that was used for enforcing QoS, but is used in many other contexts today, including virtual machines, as I just mentioned. Okay? But it's invented in sort of the networking world, but now used in many other scenarios. Okay, so I'm not going to spend too much time on other mechanisms, but there are many others that were also designed in case of networking. There were things like packet marking, where you could say, add a bit to a packet saying these packets are important, these packets are less important. So if there are queues that get filled up at routers, the routers will have priority, which says drop the less important packet, make sure the more important ones go through. right? So you might say video packets get higher priority, so they go through because you don't have time to retransmit. Other packets might be lower priority, so you can drop them and they can be retransmitted at a later time. So there are all these mechanisms that were designed. Some of them are still used today, but not for QoS, they're used for other things. Okay, so but this is something that you want to keep in mind. I won't go through all of these details, but what I will do is actually talk about video streaming again, and we'll think a little bit about these issues, how you can implement them in the context of streaming. Okay. So just to make this more concrete as to why video streaming requires timeliness constraints and what can we do, right? Because today in the internet there is no quality of service. Right? You might want a certain bandwidth, you might want end-to-end delay bound. Internet doesn't get you any of that. Yet you can stream. You watch YouTube, you watch Netflix. Occasionally there are problems, but by and large things work well. Okay, so how do you do this? Can you actually provide the illusion that you are getting good quality, even though network is best effort, doesn't give you any guarantee. Okay, so understand this. Let's look at this picture and try to see what might happen and how can you prevent certain problems from happening. Okay, so here the x-axis is time. Yes, the top line is basically a video server, a streaming server that is sending out packets. Okay, so let us assume it's 30 frames per second video. Each of those packet is 1 frame. Typically that's not the case, but let's assume each packet is 1 frame. So every 33 milliseconds you'll see the regularly spaced packets are going out over the network. Okay, so you might send packets at a steady rate. But because the network is best effort, each packet is going to see somewhat different end-to-end delays. It's not that the delay is going to be constant for every packet. Okay, some might see a little more queuing, some might see a little less queuing. So they are not going to arrive at a steady rate at the receiver. So you will see that packet 1 arrived a little after it was sent, but packet 2 saw more queuing delay. So it basically was a bigger gap. Okay, and there was a bigger gap for 3 as well, and then 4, 5 came immediately one after another. Then there was more gap. This is caused because the delay is not identical for all packets. They see this is called jitter. A jitter is variation in the delay. Okay, so even though the sender is sending things at a steady rate, because the network is best effort and sees variable delay, you are not going to receive your packets at the steady rate, even though they are sent that way. Okay. Now, if you just start playing out your video as soon as the first packet was received, what do you think is going to happen?
It'll be super choppy.
Yeah, it's going to have lots of glitches because you start playing the first frame, and then you said 33 milliseconds later you got to now play the second frame, but it hasn't even arrived. Okay, so you are going to block. Then you play the second one, the same thing happens. Then you see a good video for maybe 3 frames, and then same problem occurs over and over again. Okay, this is the state of the internet today. Okay, so how do we fix this problem? That what can we do? There's no QoS you are actually going to get, but yet we got to do something before we can fix it. Yes. Okay, so you do application level QoS, but what does that mean? What will you actually do?
You'll have a buffer and burst rate, rate taking inspection.
Right.
Your buffer is based off of that. So how much you have burst is how much time you have buffer for.
Right. So you are going to do buffering. I'm just going to simplify your answer. Okay, so you said lots of things, but all you need is buffering. So what you will do is, although data has started arriving from your player's perspective, your browser's perspective, YouTube has started sending data as soon as you say play, but you are not going to actually start playing the video. You are going to keep a memory buffer and let data accumulate. Right? So in this case, you are essentially going to start buffering and wait for the first 6 packets to arrive. Then you start playing out, because now you have some headroom, because you will now start playing out 1, 2, 3, 4, because you have to always play at a steady rate. Okay? And so long as your buffer will still have some data, you are not going to have any problem. So you will see that for the first 7 packets, there is no problem, because the 7th packet arrived at this point in time. Okay? But when you played the 8th packet, it hasn't yet arrived. Okay, so because the buffer by this time emptied, you started with the buffer of 6 packets, but you started playing them out, but there was a long delay that some packets saw. Okay, so your buffer emptied. Now you have a playback glitch. Okay? What that tells you is that buffer size was not big enough to overcome the biggest delay any packet could see. Because of trying to figure out what is the right buffering interval is important for guaranteeing good playback quality. Okay? But there is a trade-off. Okay? Because the longer you are going to buffer, the more impatient your user is going to be. Okay? You hit play and you are just waiting. Okay? And there is something spinning saying buffering. Right? So you want to see your video as soon as you hit play. Okay? But if you start playing it out too soon, you have a small buffer. Then you might see a playback glitch. If you wait too long, then users might get impatient. In the limit, you are going to wait for the entire video to arrive, then there's never going to be a playback glitch. Okay, but that's the worst possible scheme because you're going to make users wait 20 minutes to play out the clip. Right? So you want to make sure the buffer size is good enough. Many clients have no idea what the state of the network is because network state also varies over time. Okay, sometimes internet might have congestions, other times it does not. So there's no optimal buffer size. Okay? It has to be discovered automatically. So what clients will do is they'll start with a conservative buffer size. If you see a playback glitch, they'll say that was too small. They'll increase it dynamically. You will see a glitch. You'll wait for some time. Then the playback will continue. But the buffer size has increased. Hopefully, this won't happen again. If it happens again, it will be increased further. So it is actually being adjusted dynamically based on network conditions. Okay, that's what many clients are going to do. Okay? So that is essentially client buffering as a way to avoid QoS problems. So if you actually had quality of service, you would never even have had this problem because the network would have guaranteed you the data would have been sent the way it was or received the way it was sent. You would have seen it at a steady rate because you asked for a delay bound. Okay, so that means the network should actually make sure the data comes the way it was sent, but that's not how it works today because it's best effort. So you have to ensure that you have some buffering built into your client. Okay, so essentially next time you watch any YouTube video or Netflix video and you see buffering, or the word buffering appearing, that's what's actually happening because you're waiting for data to accumulate in the buffer before you can start playback. Okay. So that's one problem. But now let's look at another problem, which is what happens if packets actually get dropped, because there's no, again, being a best effort network, there's no guarantee that a packet that's sent will be received. Routers along the way are free to drop packets if they're congested. Okay, anytime there's congestion in the network, okay, queues at routers fill up and the packets get dropped, okay, because there's not enough room to put them in the queue. Okay. So here is an example where you send data in that order 1 through 16, but packets 9, 10, 11, 12 got dropped. Okay. So again, you are going now buffering is not going to help you. Okay, because we are assuming there are no retransmissions in this case. That's one thing I should say. So buffering is not going to help you. So after you hit 8, okay, you are basically going to see a gap. Okay, and then your video might resume, but maybe a small part of the video has been missed. Okay, now what do you do in this case? Okay, so here you can do many different things. One is you can add redundancy in the data to reconstruct it. That is called forward error correction. That is basically using error correcting codes. I'm not going to go into that at the moment, but what I'll show you is a much simpler scheme that uses some form of scrambling to spread your losses so you can't actually perceive them. Okay? So in this case, what happened is you lost 4 consecutive frames. Okay? To the human eye, that may be visible because you might actually see a jump in the video. It doesn't look smooth anymore. Okay? But what if, rather than sending the packets 1 through 16 in order or in sequence, you send them in this order. You send them 1, 5, 9, 3, 2, 6. Basically, you take the first packet from each of those boxes, send them in sequence, the second, third, and fourth. Okay? Now, if the loss occurs essentially when you send the third batch out, you will see what you have lost is 3, 7, 11, and 15. But when you play it out, what happens is you lose 1 frame here, 1 frame here, 1 here, and 1 here. So they get more spread out. But if you're playing 30 frames a second, your human eye can't distinguish between 29 frames and 30 frames, really. Okay? But it can actually see a consecutive set of frames, or if you are actually hearing audio, your ears are even more sensitive than your eyes. You can actually feel that there is a drop in audio quality if some audio samples get dropped. But if they're spread out, there is less perception of a problem. Okay? There's still a problem. It's just that you're trying to minimize the impact that the user sees. The experience is much better in this case than in that case. Okay? Having said that, what you have to realize is because you scrambled the sending order, you have to wait until all 16 frames are received before you play it out, because the 4th frame actually comes as the 13th frame of that sequence. Okay, so but that's okay because you may be buffering large amounts of data anyway. So you can receive them out of order, reconstruct the sequence in the buffer and play it out in right order. Okay, you're not going to play it out in that order. That would not make any sense. Right? You have to still play them out in the order 1 through 16. Okay? So this is another trick that you can use to essentially spread your losses, because there's no time to retransmit. Okay, because that is going to add further to your delay. So you're basically going to take your losses and try to spread it around so that the user cannot perceive them as much. Okay? So you use buffering, you use scrambling. There are many other techniques like that that are used in video streaming. Okay, so I'm going to spend one last slide and then we'll end here. Okay, so this is basically how things work today, okay, which is that regardless of how video streaming was designed in the early days, today all streaming is actually happening over HTTP. Okay? It's not push based, it is still pull based. Okay? And the way things work is you have a video file, you are going to chop it up into smaller segments, smaller pieces called chunks. Okay, so maybe a 1 hour file, you partition it into maybe 5-second chunks. So you'll have essentially chunks, and then your client is going to make an HTTP request for one chunk at a time. Okay, so you'll get the first 3 seconds and you will request the next 3 seconds as an HTTP request. Okay, and the next one and so on. And then the hope is that you're requesting them fast enough and they come over the network fast enough that you can still get all the data in time and play it out. Okay. That requirement has not gone away. You still need the data to arrive in time, except that in this case, the server is not pushing that data to you. You are still requesting it as separate HTTP requests. Okay. So first point is this, although server push is a more natural mode for sending video or audio data, what actually happens over the internet today is you still use pull-based protocol, specifically use HTTP to get data and play it out. Okay, that's first. The second thing is most of the data that you actually see over the internet is actually has been encoded at different quality levels, because you don't know what device the user is using to play out that video. Okay? You might be playing it out on a phone, which is small screen. You might be doing it on your laptop or desktop, bigger screen, or you may have actually putting it on your TV, which may be 40 inches. Okay? That requires much higher quality video. Okay? Now, how are you to know when you, or how is YouTube to know when user uploads their video, what device they're going to play it on? Okay? If you say let's encode it at the best resolution always, that means you'll waste a lot of network bandwidth if you are playing it at a lower, on a lower, smaller device. Okay? Not only that, if the connection is poor, you might not be able to send a high quality data and get good, regardless of buffering and all those other tricks, you might still see lots of problems. Okay, so you might have to use a lower quality version at least for the user to see something. Okay. So there are lots of issues that you have to deal with to actually get good video delivery. So what happens is every video that you might upload to any streaming service or any streaming service that provides you this kind of service will encode that at different quality levels. So here green, red and blue are low quality, medium quality, high, but there will be many more quality levels. Okay. And it's up to the client to figure out what quality level to ask for. The server is not going to know whether you are doing this on a phone or not. The client is smart enough to know it's running on a phone or some other thing, and it will, other device, it will ask for the right quality level. Furthermore, you can change the quality level during playback. So you could start with the highest quality. If you start seeing the playback glitches and buffering is not working, you could say, I'm going to drop my quality level. I'll need less data to come, so maybe it will come in a timely fashion, have less bandwidth available. So you can essentially lower and raise your quality level based on what actually is happening in the network. Okay? You might have seen when you play Netflix or YouTube, occasionally the video becomes grainy, and then the quality improves again. Okay, the reason that has happened is your client has actually requested a lower quality version of that, the next chunk, because it sees that buffers are beginning to empty. So rather than letting it empty, you just get less data by asking for a lower quality. That way you don't see a playback glitch, you just see a lower quality, but you still see smooth playback. And later on, when the network bandwidth is better and your buffers start filling up, you might say, okay, I'm going to go back to blue and give you better quality, or whatever your device needs. Okay, so all the clients are smart enough to buffer to make sure they'll ask for the right resolution and so on and so forth. Okay, so that is essentially how streaming actually is done today. over the internet. Okay, so you essentially use HTTP streaming. In fact, it's called direct adaptive streaming or HTTP. Adaptive because you can change the quality level on the fly from the client's perspective. It's called dash streaming. Okay, so we are almost out of time. I'm going to end here. Okay, and just a reminder that I will send a note about whether there will be a makeup class or not on Friday, and if so, when it will happen. Okay, so let's stop here. Yes. Yeah, just 1 second.